Error correction is the most important method in technology and learning in general. In biological evolution, it appears to be the only means of progress. One rightly speaks of the trial and error method, but this understates the importance of mistakes or errors, of the erroneous trial. All life is problem solving. All organisms are inventors and technicians, good or not so good, successful or not so successful, in solving technical problems. This is how it is among animals. Spiders, for example. Human technology solves human problems such as sewage disposal or the storage and supply of food and water as, for example, bees already have to do. Hostility to technology, such as we often find among the greens, is therefore a foolish kind of hostility to life itself, which the greens have unfortunately not realised. But the critique of technology is not foolish, of course. It is urgently necessary. Everyone is capable of it in their different ways, and most welcome to contribute. And since criticism is an occupational skill of technologists, the critique of technology is a constant preoccupation of theirs. Karl Popper, from the essay All Life is Problem Solving, from the book of the same title, All Life is Problem Solving. So welcome to the Topcast and episode 90, I think, certainly part 2 of chapter 3, Problem Solving in the Fabric of Reality. And I began there with what Karl Popper had to say about problem solving, namely all life is problem solving. And what I understand he meant by this is not only that every single thing in a human life is about problem solving. You are continually trying to solve different problems. That's not only a way in which to avoid suffering, the bad things in life, but also a way in which to enjoy life. If you had a situation where you had no problems, where you weren't trying to solve anything, then as David Deutsch says in The Beginning of Infinity, the other name for a problem-free state is death. We are constantly trying to solve the problem of how to be warmer and more comfortable, how to be more interested or interesting. What to do next is often a problem for us, how to solve a particular scientific problem, how to go about our work lives, how to go about our family and social lives, how to get out of pandemics and difficult situations we find ourselves in, how to find out which of the interesting things and opportunities that we have before us might be best for us to pursue. But of course, it's not only about humans. It's about every single living organism. So we can also take all life is problem solving too. That's literally what life is trying to do, trying to solve the problem of keeping itself in existence. Individual organisms are kind of trying to do that to some extent. Really, it's the genes trying to get themselves replicated. However, life, whether it's our human lives personally or life broadly speaking, as broadly as you can conceive it, it's about problem solving. And in part 1 of my discussion of this chapter, we eventually got to a universal scheme, which I'll put up on the screen now, a universal scheme for the solving of problems. And this scheme that David is setting out, it's a practical vision for problem solving. It's a universal program of a kind. As he will say, this applies to every topic, no matter the subject matter. And of course it applies importantly to people's personal lives, to business, to something like police detective work, as well as science, history, mathematics, philosophy, and so on. What separates science in this scheme is the existence of crucial experimental testing. So let's pick it up where David writes, quote, "What I have described so far applies to all problem solving, whatever the subject matter or techniques of rational criticism that are involved. Scientific problem solving always includes a particular method of rational criticism, namely experimental testing, where 2 or more rival theories make conflicting predictions about the outcome of an experiment. The experiment is performed, and the theory or theories that made false predictions are abandoned. The very construction of scientific conjectures is focused on finding explanations that have experimentally testable predictions. Ideally, we are always seeking crucial experimental tests, experiments whose outcomes, whatever they are, will falsify one or more of the contending theories." Now, to learn more about that idea of falsifying one or more, ideally all the other rivals, leaving only one standing, then consult David's seminal paper, titled, in part at least, The Logic of Experimental Tests, or my own guide to the paper, which is simply called The Philosophy of Science. I called it that because it seemed to me at the time, and it still does, that this was the crown jewel so far as that subject, the philosophy of science, is concerned. It takes Galilei, and his writings, his work on sementi or trials, up through Francis Bacon, who, along with Locke, pioneered empiricism, through to Popper and his work on demarcation and conjectural knowledge, and finally all the way up to David Deutsch and his hard-to-vary good explanations and the nature of what's called a crucial experimental test. Okay, so let's keep going. David writes, "This process is illustrated in Figure 3.3. Whether or not observations were involved in the instigating problem, stage 1, and whether or not in stage 2 the contending theories were specifically designed to be tested experimentally, it is in this critical phase of scientific discovery, stage 3, that experimental tests play the decisive and characteristic role. That role is to render some of the contending theories unsatisfactory by revealing that their explanations lead to false predictions." That bears repeating. I'll say it again. That role, the role of experimental tests, is to render some of the contending theories unsatisfactory by revealing that their explanations lead to false predictions. Here I must mention an asymmetry which is important in the philosophy and methodology of science, the asymmetry between experimental refutation and experimental confirmation. Whereas an incorrect prediction automatically renders the underlying explanation unsatisfactory, a correct prediction says nothing at all about the underlying explanation. Okay, just pausing there, my reflection. When you have this disagreement between an experimental result, an incorrect prediction in other words, and the theory itself, which makes that prediction, so you have this clash between an experimental result and a theory, then the underlying explanation is unsatisfactory. Now, it doesn't mean that the theory itself is necessarily logically wrong. It means the underlying explanation, which is the explanation of what's going on in the experiment, coupled with what's going on with the theory. So these two things together, there's a conflict there. So the explanation of the whole thing is unsatisfactory. Now, the standard way of understanding this is to, of course, say, well, the experimental result has falsified the theory. And that is typically how science works. But it's also an ideal about how science works. It could be the case that the experiment is flawed. But whatever the case, whether it's the experiment that's flawed or whether it's the theory that's flawed, the underlying explanation of the conjunction of those two things is flawed. And that's what David is saying here. Now, this also bears repeating, okay, that last thing that I read. A correct prediction says nothing at all about the underlying explanation. Such an important point, easily missed by lay people in science, but sometimes scientists themselves. There is this asymmetry, as David has said there, between experimental refutation and experimental confirmation. And we might, without any loss of meaning, simply add the word apparent there. It is an apparent confirmation whenever you see a confirmation. After all, what does it mean to confirm something? Well, philosophically, at absolute worst, putting it in its worst possible light, so to speak, confirm or a confirmation could mean to show as actually being true something or other. So if you confirm a theory by observation, you have shown that theory to be true, like finally true. And the way that people talk, okay, I was listening to, I know he's not a scientist, but, somebody who has studied some philosophy, and I think represents common understandings on this thing, is the comedian Ricky Gervais. Now, he talks in this way. He talks about confirming a theory and confirming a theory is true and knowing that something is true and so on and so forth. And I think I'm just using him because that's a good example of the way I think an overwhelming majority of people think on these topics. And he's someone with actual philosophical training and someone who indeed talks to prominent scientists and others. So it could mean that. It could mean that confirm means to show something as actually true, which any Popperian will, of course, say, well, this is impossible. This is an impossible standard, so we can throw confirm into the bin. We don't need it. But if I was to try and steelman that position, that confirm doesn't need to mean something like show absolutely and finally true, it could mean something like this observation conforms to that theory and therefore lends credence to it, which is a fancy way of kind of saying shows it more likely to be true without showing it finally true, which is, of course, an inductivist mistake of a kind. Now, Popper himself in various places, Logic of Scientific Discovery, Objective Knowledge, various other things in places that he's written about this, he makes a big deal about this, about the whole idea of rejecting confirmation. And of course, he's right to do so. But it seems to me that he wants to still have the word, still meet his opposition halfway. And so he comes up with this word corroborate. And so he uses the word corroborate instead of confirm, and says, well, we can use the idea of experiments that agree with a particular theory corroborate the theory. And of course, if you go to a dictionary and you look up what corroborate means, it means something like confirm. So I don't think it gets him very far. Because whether it's confirm or corroborate, it seems to imply some kind of possibility of support for a theory. And you can't support a theory, by which we mean the theory isn't justified. The theory isn't absolutely true in any way, shape or form. The best that I can say for what Popper is saying about corroboration in this case is that he's kind of talking about how some theories really do stick their neck out in a way and then don't get falsified by experiment, which can be telling. You know, it says something, it's not completely contentless, that information, when a particular theory makes a risky prediction and gets the prediction right, or rather doesn't get falsified by the experiment is the way I would better say it. So for example, the classic case of testing how much light bends during a solar eclipse, you know, this is Eddington's experiment to distinguish between whether general relativity is the best theory or Newtonian gravity. On this view about corroboration, you would say, well, general relativity is corroborated by the correct prediction about how much the light bends. I don't know that it adds that much, given what Popper says elsewhere about how, well, the best explanation is, of course, general relativity. And once that experiment, that crucial test, Eddington's experiment, refutes, shows as inadequate Newton's theory of gravity, therefore we say it falsifies Newton's theory of gravity, you don't need to use this word confirm, corroborate, support, anything like that, because the only theory you have left standing is general relativity. There are no rivals. It doesn't need support because, heck, it's the only one we've got. What more do you want than the best theory, the only theory that is there before you with regards to what the nature of gravity is? It can do all the explanatory work that you need, and it can do all the predictive work that you need until such time as you find a problem with it. So I don't think any of this is needed. Again, I think that Popper's just conceding a certain amount of ground to his opponents politely so that the conversation can keep on going, because they, of course, are absolutely enamored by this idea of justification and support and confirmation, and so he's thrown them a bone, I suppose. Perhaps. It'd be good to be able to ask him. The fact is that in many of these cases we have, in the case of gravity, we have an explanation of gravity, an existing best explanation of gravity. Emphasis on the an, okay? There's not multiple excellent explanations of gravity. There's one. So it doesn't matter how often it gets corroborated, you know, it makes these risky predictions because it's already the only existing theory. So it doesn't need more support. It just is the theory. Now, is it true? Is it finally true? No, we've been through that. Of course, it's not finally true. It's just the best. It contains some truth about reality. But, you know, how does being consistent with predictions help? Well, let's go back to the book. David writes, quote, "Shoddy explanations that yield correct predictions are two a penny, as UFO enthusiasts, conspiracy theorists, and pseudoscientists of every variety should, but never do, bear in mind." Okay, pausing there, just a little comment on that bit. So, for example, a person who believes aliens are visiting us will be able to confirm, or corroborate, if you like, their belief that, namely, the pictures of UFOs that are sometimes published are consistent with the existence of aliens visiting Earth from another galaxy via spacecraft that travel beyond the speed of light or something like that. They don't look for refutations. They look for consistency with their already existing theory. They look for confirmation. Now, some scientists and some people who regard themselves as critical thinkers call this an example of confirmation bias. But of course, I would say it's just the error of thinking that confirmation is even a thing at all. Many, many scientists do indeed think that it is a thing. And I think that's a kind of bias of a kind. They think that too much confirmation is a bad thing, but just the right amount of confirmation is a good thing. That's possible. It's possible to have a little bit of confirmation, but not too much confirmation. Then you have confirmation bias. So there's almost like there's an ideal amount of confirmation on this view. Bayesian epistemology is kind of like this. It says that some stuff is a confirmation of the theory, not a finally true confirmation of a theory, just a probabilistic confirmation of the theory. And the more you have confirmation, the more confident you become that this particular theory is the correct theory. We don't usually need that because, again, we only ever have one good explanation at any given time. And in the rare cases where we have two, then we do a crucial test, ruling out one of them and holding up the one as the explanation, not the finally true explanation. I'm repeating myself. So, whatever the case, what we're after are refutations where we can get them, not confirmations, because confirmation is impossible. Back to the book, David writes, quote, "If a theory about observable events is untestable, that is, if no possible observation would rule it out, then it cannot by itself explain why those events happen in the way they are observed to and not in some other way. For example, the angel theory of planetary motion is untestable because no matter how planets moved, that motion could be attributed to angels. Therefore, the angel theory cannot explain the particular motions we see, unless it is supplemented by an independent theory of how angels move. That is why there is a methodological rule in science which says that once an experimentally testable theory has passed the appropriate tests, any less testable rival theories about the same phenomena are summarily rejected, for their explanations are bound to be inferior. This rule is often cited as distinguishing science from other types of knowledge creation. But if we take the view that science is about explanations, we see that this rule really is a special case of something that applies naturally to all problem solving. Theories that are capable of giving more detailed explanations are automatically preferred. That bears repeating again. Theories that are capable of giving more detailed explanations are automatically preferred. They are preferred for two reasons. One is that a theory that sticks its neck out by being more specific about more phenomena opens up itself and its rivals to more forms of criticism, and therefore has more chance of taking the problem-solving process forward. The second is simply that if such a theory survives the criticism, it leaves less unexplained, which is the object of the exercise. Okay, pausing there and an example. I'll go to my trope example. Newtonian gravity said that gravity is this force that varies as the product of the masses involved, divided by the square of the distance between the masses. And in stating something true about gravity, something approximately true about gravity, it reached beyond whatever Newton was specifically interested in, the particular problem he was interested in, across the whole solar system, across the galaxy, to every single where in the universe and every single when in the universe. It reached into how the tides work and how planets moved and how rocks fell to the ground when they were dropped and so on and so forth. However, it could not explain, certainly not adequately, things like modern day examples of gravitational lensing, or the existence of neutron stars, or black holes, or the precession of orbits, or gravitational waves, or if you want to get really fancy, lens-thirring frame dragging, which is where space-time itself is literally dragged by a massive body when it's rotating. Much less all the stuff that couldn't even be imagined in the previous paradigm, the previous idea of how physics worked, gravity as well as space and time. You couldn't even imagine things like the relativity of simultaneity, length contraction and time dilation. So all those phenomena amount to predictions of a kind, given general relativity, arising out of a far more detailed explanation of the nature of gravity in general relativity over Newtonian gravity, which was less detailed. It, general relativity, sticks its neck out in many directions. Or you can think modern medicine compared to folk or ancient or pseudo-scientific nostrums. Drink this herbal tea or wear this magic pendant to ward off your illness is one thing, one level of non-explanation, so to speak. But take this paracetamol because it inhibits prostaglandin synthesis, preventing the creation of enzymes that cause pain receptors to be activated, is something else entirely, especially when it works more often than not over those nostrums. Okay, back to the book. And David writes, I have already remarked that even in science, most criticism does not consist of experimental testing. That is because most scientific criticism is directed not at a theory's predictions, but directly at the underlying explanations. Testing the predictions is just an indirect way, albeit an exceptionally powerful one when available, of testing the explanations. In Chapter 1, I gave the example of the grass cure, the theory that eating a kilogram of grass is a cure for the common cold. That theory, and an infinity of others of the same ilk, are readily testable. But we can criticise and reject them without bothering to do any experiments purely on the grounds that they explain no more than the prevailing theories which they contradict, yet make new, unexplained assertions. The stages of a scientific discovery, shown in Figure 3.3, are seldom completed in sequence at the first attempt. There is usually repeated backtracking before each stage is completed, or rather solved, for each stage may present a problem whose solution itself requires all 5 stages of a subsidiary problem-solving process. Just pausing there. Yes, so my reflection on this is that that scheme, or any scheme that you want to write out, is subject to revision and modification within actual science as it's practiced. And so there's no real method of science. You're taught this in school, follow the scientific method. People talk about the scientific method, the method, as if there is one way of doing things and one way of reaching discovery. We know this isn't true because we all know stories of so-called serendipity in science. I think too much is often made of serendipity. The people that make the biological breakthroughs are often biologists, and that's not mere luck that they're biologists. They've made the conscious choice to go into that area. But you speak to biologists about famous cases, for example, the discovery of penicillin, let's say, is the trope example, where luck was apparently involved. And how does luck feature into this scientific method? Well, the scientific method really is about the methods of criticism. Putting all that aside, I remember one of the first essays I ever wrote on the philosophy of science was in response to a question, which I cannot remember what the question was, about the logic of scientific discovery, Popper's first book. And it's not a great inroad to Popper's work, as I think I might have commented on here before. It's very technical, it's dense, it's not particularly an enjoyable read like so many of his other ones are. They're so much more clear. And especially as a person who was very new to philosophy, reading any kind of philosophy was a bit of a struggle. But in my essay, I did manage to conclude that, in a sense, Popper's own title of his work was, in a sense, misleading, because there was no logic to scientific discovery, if you, by what you mean by logic, is something more like a deductive process. Of course, he calls it a hypothetico-deductive process because it's kind of the use of what's called modus tollens, which is where it's refutation. Okay, if the theory leads to a particular prediction and the prediction turns out to be false, then the theory can show itself to be false. But whatever the case, it's not like you're putting observations in at the front of this scientific method and getting out the end scientific theories. That kind of program just doesn't work. So what you're taught in school about write down your observations and at the end of it reach a conclusion, no. That you have to start with a guess of some sort, and the guess should be an explanation of some kind. But when I wrote this essay, happily for me, the professor seemed to agree. The point here is that David is pointing out what Popper does, that creativity in science is messy and not formulaic. There are heuristics that one might apply. Of course, experimental testing is essential to the whole project of demarcating science from everything else, but you're going to go back and forth between these stages of what might be referred to as cycles of creativity and criticism. And only at the end of all these cycles might you get something called scientific knowledge at the end of it. Like looking at the scheme here, we've got the 5 stages. Problem. Well, number one, how do we know that we've got a problem in the first place? That takes a certain amount of creativity of recognizing, of seeing before you. You have a theory and you have an observation, and these things don't seem to agree with each other. But you have to creatively conjecture what's going on before you as to whether or not that really is a problem, or whether or not you've simply made a mistake, which is still a problem. Step 2 is more creativity, conjecturing a solution. This can be the hardest part of all of the entire scientific exercise. That even if you do find this problem, then being able to solve the problem, well, that's a whole other step. That's a whole other level. Many, many physicists might have observed that Mercury's orbit wasn't being correctly predicted by Newtonian gravity. They could all agree and check for themselves that this prediction seemed to be inaccurate. And they were coming up with conjectured solutions, some of which included other planets that were yet to be observed, perturbing the orbit of Mercury. But it took the genius of Einstein to solve it. Lots of scientists might have thought, how do we have this diversity of species on the planet? Is there this thing called evolution? But it took the genius of Darwin to figure out there's this thing called natural selection, evolution by natural selection, so on and so forth. When we get to part 3, and I'm going to mention more on this later, we've got criticism including experimental tests. That can require an equal amount of creativity. Simply devising the experiment can be one of the hardest parts of this entire enterprise. I asked David a question about this, actually, in one of my questions for David. And he talked about how, yes, people underestimate just how difficult some experiments can be to do. So anyway, all this entire scheme, this 1 through 5 scheme, all of it requires a significant amount of creativity. There's no formula to it, and you're going to go backwards and forwards between thinking there's a problem, recognizing perhaps there's not a problem, thinking there's a problem again, coming up with a solution, realizing the solution doesn't seem to work because you've conjectured a particular kind of criticism, and the criticism has been valid or invalid, and so it goes. I mean, it can be a very messy process, which of course all brings us to the idea that scientists and scientific progress needs time. It can't be this standard kind of a job that other people might be in, where you're working in a factory and you're doing a similar thing over and over again day after day, or even in the media where you're just reporting on things that you see in front of you and coming up with a story, and the stories are going to move on tomorrow. So it doesn't matter if you made a mistake yesterday, you just keep moving forward. But science can't be quite like that. It's very difficult to try and eke out a little bit of truth in the mess of falsehoods and errors that you're surrounded with. That can be hard. And so David talks a lot about this going backwards and forwards, but I'm going to skip most of that part where he discusses this moving between the stages that he has here, except to mention that also he talks about stage 3 there, which is so important with the idea of criticism here in science. You might need to invent new modes of criticism. There might have to be a new way of coming up with a scientific theory, as I flagged earlier. And so that can just be extremely difficult to do. And that can lead to sub-problems. The sub-problem of how to come up with the new experiment, how to figure out how to solve the problems in the experiment. So often in physics, at least, it's very difficult to see the effect that you want to see. There's the famous Michelson-Morley experiment to try and detect the so-called ether, this material through which light waves would propagate. It used, among other things, an interferometer. Now, putting aside exactly what the experiment sought to establish and failed to establish, the existence of the ether, the ether wind rather, just trying to set the whole thing up to get it to work in the first place, the engineering problems were so difficult. I think the entire experiment had to sit in a bath of mercury, liquid mercury. And because it's an interferometer, it's looking at interference effects with light. That's extremely difficult. Trust me from experience that you try and do experiments on the interference of light, and it's very difficult to see, let alone measure what's going on. It's a very subtle effect. So much in physics is about subtle effects, difficult to observe effects. And to pick them up, you often need to invent new instrumentation or faster computers. My own very, very modest inroads into doing a kind of experiment required me to figure out whether or not these two particular galaxies were going to merge or pass through one another. And the number of parameters that you needed to change for each galaxy kind of ballooned exponentially the more accurate you wanted your prediction to be. And in particular, the more stars you had in your simulated galaxies, the higher the computing power that you needed, which again is more ways of changing the experiment. And so more creativity is required in order to try and use a slower computer in order to figure out what an otherwise faster computer might have been able to tell you. And so this is kind of a sub-problem. So I'll pick it up where David says, quote, "Not only is there constant backtracking, but the many subproblems all remain simultaneously active and are addressed opportunistically. It is only when the discovery is complete that a fairly sequential argument in a pattern something like Figure 3.3 can be presented. It can begin with the latest and best version of the problem, then it can show how some of the rejected theories fail criticism. Then it can set out the winning theory and say why it survives criticism. Then it can explain how one copes without the superseded theory, and finally it can point out some of the new problems that this discovery creates or allows for. While a problem is still in the process of being solved, we are dealing with a large, heterogeneous set of ideas, theories and criteria, with many variants of each, all competing for survival. There is a continual turnover of theories as they are altered or replaced by new ones. So all the theories are being subjected to variation and selection according to criteria, which are themselves subject to variation and selection. The whole process resembles biological evolution. A problem is like an ecological niche, and a theory is like a gene or a species which is being tested for viability in that niche, or niche. Variants of theories, like genetic mutations, are continually being created, and less successful variants become extinct when more successful variants take over. Success is the ability to survive repeatedly under the selective pressures, criticisms brought to bear in that niche. And the criteria for that criticism depend partly on the physical characteristics of the niche and partly on the attributes of other genes and species, i.e. other ideas, that are already present there. The new worldview may be implicit in a theory that solves a problem, and the distinctive feature of a new species that it takes over a niche are emergent properties of the problem or niche. In other words, obtaining solutions is inherently complex. There is no simple way of discovering the true nature of planets, given, say, a critique of the celestial sphere theory and some additional observations, just as there is no single way of designing the DNA of a koala bear, given the properties of eucalyptus trees. Just pausing there. I know any Australians listening to this will balk at the idea of a koala bear. We are metaphorically bashed over the head as children that koalas are not bears, but we can forgive this. The use is kind of like teddy bear. I mean, a teddy is not a bear either, but nonetheless, I think it's quite fine to use that terminology. Going on, David writes, quote, "Evolution or trial and error, especially the focused, purposeful form of trial and error called scientific discovery, are the only ways. For this reason, Popper called his theory that knowledge can grow only by conjecture and refutation in the manner of Figure 3.3 an evolutionary epistemology. This is an important unifying insight, and we shall see that there are other connections between these two strands." What are the strands? Just to me here, the strands are epistemology and biological evolution, or evolution by natural selection. Okay, but David goes on to say, quote, "But I do not want to overstate the similarities between scientific discovery and biological evolution, for there are important differences too. One difference is that in biology, variations or mutations are random, blind, purposeless, while in human problem solving, the creation of new conjectures is itself a complex, knowledge-laden process driven by the intentions of the people concerned. Perhaps an even more important difference is that there is no biological equivalent of argument. All conjectures have to be tested experimentally, which is one reason why biological evolution is slower and less efficient by an astronomically large factor." Pausing there, just my reflection on that, or just rather my emphasis here, because conjectures, which in biology amount to gene mutations, must themselves be tested individually. So each time an organism, the variation between organisms within a species amount to a kind of gene mutation from one species to another, each of them gets tested in the environment. And because each of them are getting tested by the measure that the organism itself does not survive, so it goes through its natural life or whatever, okay, which usually some years, that's a very slow process. But as David has been pains to say here, we criticize explanations without ever needing to actually test them necessarily in the real world so often. Whereas biological evolution only ever does that, testing in the real world. Okay, we can cut through and just look at the quality of the explanation rather than constructing the experiment, which, as I've just said and explained, itself is a creative process which requires quite a lot of effort to do. It's not trivial to do, especially these days, scientific experiments. Back to the book. Nevertheless, the link between these two sorts of process is far more than mere analogy. They are two of my four intimately related main strands of explanation of the fabric of reality. Both in science and in biological evolution, evolutionary success depends on the creation and survival of objective knowledge, which in biology is called adaptation. That is, the ability of a theory or a gene to survive in a niche is not a haphazard function of its structure, but depends on whether enough true and useful information about the niche is implicitly or explicitly encoded there. I shall say more about this in Chapter 8. Okay, now I'm skipping a small amount, and I'm going to where David says, quote, "Take a moment to compare figures 3.1 and 3.3. Look how different these two conceptions of the scientific process are. Inductivism is observation and prediction based, whereas in reality, science is problem and explanation based. Inductivism supposes that theories are somehow extracted or distilled from observations, or are justified by them. Whereas in fact, theories begin as unjustified conjectures in someone's mind, which typically precede the observations that rule out rival theories. Inductivism seeks to justify predictions as likely to hold in the future. Problem solving justifies an explanation as being better than other explanations available in the present. Inductivism is a dangerous and recurring source of many sorts of error, because it is superficially so plausible. But it is not true. I'll say that again. Inductivism is a dangerous and recurring source of many sorts of errors because it is superficially so plausible. Okay, and then David goes on to say, quote, "When we succeed in solving a problem, scientific or otherwise, we end up with a set of theories which, though they are not problem-free, we find preferable to the theories we started with. What new attributes the new theories will have, therefore depends on what we saw as the deficiencies in our original theories, that is, on what the problem was. Science is characterized by its problems as well as by its method. Astrologers who solve the problem of how to cast more intriguing horoscopes without risking being proved wrong are unlikely to have created much that deserves to be called scientific knowledge, even if they have used genuine scientific methods, such as market research, and are themselves quite satisfied with the solution. The problem in genuine science is always to understand some aspect of the fabric of reality by finding explanations that are as broad and deep and as true and specific as possible. When we think that we have solved a problem, we naturally adopt our new set of theories in preference to the old set. That is why science, regarded as explanation-seeking and problem-solving, raises no problem of induction. There is no mystery about why we should feel compelled, tentatively, to accept an explanation when it is the best explanation we can think of." End quote. End of the chapter there. Isn't that brilliant there in that last paragraph? We have encapsulated so much which is in the beginning of infinity, so much that is in Popper's work, so much that today motivates people who follow in this particular mould of the way in which we understand how knowledge is created. Science is the process, the methodology of science. Science, its very self, seems to be debased, denuded of its character by people who see it as a purely predictive exercise. And again, as I've said before, this seems to happen only in physics. I mean, it's not like the geologists are out there only concerned about predicting what minerals are where, what rocks are where. They want to understand why they're there in the first place. Astrophysicists want to understand why it is that galaxies have the shapes that they do, why it is in cosmology that the universe is behaving the way that it is, whether it's going to expand forever at an accelerating rate or what's going to happen in the future and why. What is the nature of this dark energy? Not that it's just there and it's causing this particular phenomena and that particular phenomena allows us to make a prediction. The prediction is only a small part of what we're really interested in science. We're interested in understanding reality, which requires good, hard-to-vary explanations. And that's all here. Another way of putting that is, of course, it's about problem solving. Okay, so that's where I'll end it today. Thank you to all of my supporters. If you'd like to join them in supporting the podcast, then look up Patreon, Talkcast, or go to bretthall.org where there is a donate button. Now, I'll just leave you before I say goodbye with a final quote from David Deutsch about the centrality of problems not merely to science, but to the entire project of knowledge creation and the search for good explanations. Until next time, bye-bye.
And with problems that we are not aware of yet, the ability to put right, not the sheer good luck of avoiding indefinitely, is our only hope, not just of solving problems, but of survival. So, take 2 stone tablets and carve on them. On one of them, carve "Problems are soluble." And on the other one, carve "Problems are inevitable." Thank you.